The following is the video solution from JSDT Solutions. Question 11 says, in the diagram, A, B, G, and F lie on the larger circle. A smaller circle is drawn to touch the larger circle internally at A. So we have that circle over there. EA is a common tangent to both circles, as you can see with the bigger circle and the smaller circle. EBCF is a tangent to the smaller circle. So that is that over there. That's a tangent to this circle only. And of course, it's a tangent at C. AC is produced to G. AF cuts the smaller circle at D, as we can see there. AF just cuts in there. And A, B, C, D, and GF are drawn. So these are just lines that are drawn. Question 11.1 says, if EAG is equal to X, determine with reasons 4 other angles that are equal to X. So EAG is this angle over here, E to A to G. So this angle here is X. 4 other angles that would be equal to X. Okay, so they already put EAG where we have a tangent, okay, the tangent to both circles. So we can use it like that. If this is a tangent to both circles, then all that means is the angle between the tangent and the chord, let's use the smaller circle first, and the chord in the smaller circle would be equal to the angle supported by that chord, and that would be this angle D1. See, supported by that chord. So we can go ahead and start with that. We can tell them that angle D1 is equal to angle EAG, so EAG, which is therefore equal to X. Okay, so wherever we find these, we should just put down X so that we know that we have found that. So this is now also X. Okay, where else? Because it is a tangent, a common tangent to the smaller and the bigger circle. So it's the angle between this tangent and the chord in the bigger circle that is equal to the angle supported by that same chord. So this angle AFG. So that is what will be equal to X. And we can just note that down as well. So it's also equal to EAG, which is equal to X. And both of them are because of the tan chord theorem. So we'll just also put those reasons down. Okay, let's see what else we can see in this diagram. So given everything that we have, we don't have a diameter, we don't really have radii, nothing like that. However, we do have this. So remember how this is a tangent, but we also have another tangent to the smaller circle. This EC is also a tangent. And we know that tangents drawn from the same point are equal. So if these two lines are equal, then it means that the angles opposite their equal sides, that angle and that angle, are also equal. So that would prove that angle C1 is also equal to X. So with this one, let's go ahead and state the sides that were equal that made these angles equal. So AE is equal to CE first, and that is because of tangents from the same point, okay? So tangents from the same point are equal, therefore these two angles are equal. Angle C1 is equal to angle EAG as well, which is also equal to X. And the reason for that would be angles opposite equal sides are equal. Okay, so that is the third one that is equal. And then we need one more. Okay, so this one is quite simple. You see how these lines cross, they intersect like that. So we have vertically opposite angles. So angle C4 is also equal to X because it's equal to angle C1. So we can just tell them that angle C4 is equal to angle C1, which is also equal to X. And this is because of vertically opposite angles are equal. So vertically opposite angles is fine. And there we go. Okay, we've got 4 angles that are equal to X. And you just need to make sure that it stays in the diagram because it will help you with the next questions. Okay, and that is it for 11.1. Question 11.2 says, prove that AG times AD equals AC times AF. So what we have to do here is just find those lines so that we can make sense of it. So AG is this line over here. AD is this line over here. AC is this one, and AF is this. So from that, you can clearly see that they use the proportionality theorem. For them to have used that, it means that CD has to be parallel to GF. So can we see a solid reason why those two will be parallel? Yes, okay, angle D1 is equal to angle F that. Okay, it's not really F1, but it's AFG. So since they're equal, what we actually have there are corresponding angles. If you have corresponding angles and they happen to be equal, it makes your lines parallel. Okay, so let's go ahead and state that first. Okay, so there we go. AFG equals angle D1, which is still X. And therefore, those two lines are parallel, CD and GF, because we have corresponding angles that are equal. Okay, so now that they are parallel, we can go ahead and use the proportionality theorem, because we can see from the lines they are using, they clearly use that theorem. So we're going to take AC over AG, and we'll say that is equal to AD over AF, and it's because of the proportionality theorem. And then we can just tell them this is because of the proportionality theorem or prop theorem. Okay, now we just have to make it look like that. So do you see that they just cross multiplied? So they said AG multiplied by AD, and then they got AG times AD is equal to, and then they multiplied across like that. So AC multiplied by AF. And there we go. That is just the conclusion. We're finally proven what they asked us to prove. Okay, and that is answer to 11.2. Question 11.3 says, prove that triangle AGF is similar to triangle ABC. So let's go ahead and mark these triangles. So here is triangle AGF, and then triangle ABC is this one over here. How can we prove that these two triangles are similar? Okay, so first we can see that they have an equal angle, X and X. However, if you look at it like this, look at AF. This is a chord that is supporting angle B2 and angle G at the circumference of the bigger circle. So they would be equal. Okay, so you already have two angles equal in these triangles. Therefore, the third angle by default will be equal. So there we go. That's how we would prove that. So let's introduce our triangles first and then get on with proving it. So in triangle AGF and triangle ABC, and we're going to state everything that is equal. So we first know that angle C1 and angle AFG are already equal since they're both equal to X. And let's state that. And this has already been proven. So we can just tell them it's been proven. And then what else? We had these two angles being equal. This is equal to this because of the angles in the same segment are equal. So let's go ahead and tell them that, and I'm going to name the bigger one first. So AGF is equal to angle B2. So AGF equals angle B2. And that is because of angles in the same segment. Okay, and now that we have that, we can also just finally conclude that the third angle in each triangle would be equal by default because the sum of angles in a triangle must add up to 180 degrees. So if those two are already equal and those two are already equal, then by default, the remaining two will be equal. So angle A2 would be equal to angle A3. We can tell them that angle A3 is therefore equal to angle A2. And this is because it is the third angle in a triangle. Okay, and that proves that they are similar since their corresponding angles are all equal. So triangle AGF is therefore similar to triangle ABC. Okay, and the reason they are similar is because of angle, angle, angle. Three sets of angles that are equal. And you have to state this because this is not the only way that triangles can be similar. They can also be similar if their sides are in proportion. But they didn't give us any length, so we don't have to focus on that. Okay, so that is it for 11.3. Moving on to the next question. Question 11.4 says, prove that GF squared is equal to BC times FC. So when you see these kind of things, we're going to have to find out where these lines are coming from. So let's get our diagram and make sure to update it. I've already updated this diagram. So you see that these two are equal. We have all the x's that are equal there. And these two angles, A2 and A3, are equal. So looking at that, let's just see the sides that they are using. So we have FG or GF squared, meaning it was used twice. Now it's over here. The only two places it could have been used is in this triangle here and in the bigger triangle, because do you see that in those two triangles, it is one of the sides of those triangles. Okay, so we'll look at it as it was probably used for those two triangles. And then we have BC. So BC is over here. And this was probably used because of this triangle ABC. And then FC, let's just see, FC is over here. Okay, so it seems like they used this little triangle. And then AF is over there. So we can see that the bigger triangle was also used, definitely. And then we have AD as well. So AD, where does AD fall? AD is just here. So they probably used this triangle. Okay, with the triangles that we're looking at, you see that these triangles have a lot of similarity. See, we already know that these two triangles are similar. And we know by default, okay, because of the proportionality theorem, we know that these two triangles will be similar. Okay, these two, they will definitely be similar because we have corresponding angles and a common angle, angle A3. And now we can also see that these two would be similar. See, like that, because they have vertically opposite angles. They've got these two being equal, and they've just got a third angle. Okay, so all three would probably be similar, and then we'll see how we can get those dimensions. The previous question usually has a lot to do with the next question. Let's look at the previous question. Does it have sides that we need here? The previous question was using AGF and ABC. Looking at those sides, you see that we have FG. We actually do have that. That is something that we should look for. But here, the FG goes with BC. Okay, do we have BC here? Yes, it's also one of the sides that is highlighted. Also see that AF as well and AC. Okay, AC is not really needed, but we do need AF. So that may be helpful. So we can use those proportions over each other. Let's just see what we get with that. So my plan here is actually to take advantage of this GF because it appears twice. If we could get dimensions that include GF and then make GF the subject in each, then multiply them together to get GF squared, then this could end up being a scenario that we have. But of course, we're going to have to carefully monitor it so we don't have to, do a whole trial and error. Okay, so because this one has FG, which is something we're looking for, we need that twice. Let's go ahead and use that. So we're going to say, to use it like this, we can say FG or GF, right? So it was GF here, we can leave it like that. GF, so when you take the second and last, you have to take the second and last in the second triangle as well. So GF over BC would be equal to AF over AC. Okay, so the reason was because we had those two being similar. Okay, so now let's go ahead and make GF the subject. So we have GF is equal to, and if you take BC over, it will go to the numerator. Okay, just transpose it. So it is AF times BC over AC. Okay, we'll monitor this. The thing about AC is we don't really need AC because it's not one of the sites highlighted. It's not one of the sites that was included here. So we have to find a way to get rid of AC. And the only way to get rid of AC is to get another side with AC. Okay, but depending on where AC is, it can cancel. For example, if you had AC over something times something over AC, they would cancel. So it's not necessarily that big of a problem as long as we just get something with AC that can help to cancel that one. Okay, now let's just compare this with what we're supposed to prove. We've got 1 GF. That is great. Okay, we've got 1 GF. We have a BC, which is what they also have, a BC, and FC we don't have. So we need to find something with FC, and AF, we actually do have AF. So AF is there, and AD, we do not have AD. So let's look for a triangle with FC, AD, but remember they should still be GF and AC in it. So these are the sides that we're looking for. We're looking for a triangle with FC, with AD, with AC, because it needs to be able to cancel that one there since we do not need it. It's not in here. And we need another GF to create GF squared. So we need GF. Let's see. Are there any triangles that fit these? Okay, so let's just remove these and just see. We need an FC. So FC is this. We need an AD here. We need an AC. So you can already see this triangle is probably involved. And GF. We need a GF. Okay, so it's these two triangles that we can actually use to form this. We can use this triangle here and this triangle here. For us to be able to use them together, to use their proportions together, they need to be similar. Okay, so they are actually similar. As you can see, we've got an X, we have an X. And then we actually have two angles equal to each other here because these are corresponding angles, okay? They form an F with the parallel lines. So we have two angles equal to each other there. And then the third angle will be equal by default. So we can state that these two are similar because they have corresponding angles that are all equal. Okay, they never asked us, we're not proving that the triangles are equal, we're just showing them that they are and giving them a reason for that. Okay, so let's just ensure we name it in the correct order. You see the black line and the black line together and the red and the red. So if you named it as DCA, then you need to name this as CGF. Or we can just call it ADC and FCG. That's fine. Okay, so triangle ADC is similar to triangle FCG, and that's because all their corresponding angles are equal. Okay, so with these, we know what we're looking for. Let's just focus on those. We need one with FC. Okay, there, we've got one with FC. So if you take FC, by default, you need to take the side that corresponds in this triangle. That's the first and second letter, so we also have to take the first and second letter. So this is going to be AD over FC. Okay, and this is equal to, let's find out what it's equal to. We also need AC and GF. So let's focus on getting the GF. If we take GF, do you see that GF appears here? So you have to take the first and second letter with the first and second letter, and that actually works out perfectly. So this is equal to, and we can just follow that. That's going to be AC over FG. Okay, let's go ahead and we can call it GF just to make it the same. Okay, now we can go ahead and just make these the subject. So make that the subject. This is already the subject here. And then we're going to multiply them together. Okay, so now we can just cross multiply. It's better to cross multiply so we just avoid any mistakes. So we need GF multiplied by AD is equal to, and then FC times AC. So FC times AC. And then we'll make GF the subject because we just want that to be on its own. So we'll divide both hand sides by AD. So GF is equal to FC times AC over AD. Okay. And now we have GF as the subject. Okay, so now we can form GF squared. So we can go ahead and call that equation 1. And that's our second equation. And we're multiplying them. So equation 1 times equation 2. And so that's going to be left-hand side times left and right times right. So that's GF times GF. GF times GF is equal to, and then we're taking all of this multiplied by the right-hand side of GF in equation 2. Okay, so there we go. So this is therefore equal to, so we have GF squared is equal to, and you see here that AC, the AC that we were trying to get out, by adding another AC that would be in the numerator, we would cancel that, okay, because they would multiply. And then now we can just put it in the same order because now we have the same things. So we have BC, FC, AF. So there's BC, there's FC and AF. So we'll say BC times FC times AF all over AD. And that is our answer. So there we go. Okay, so that one always takes a little bit of thinking, but that is one way we can solve it. And that is the end of question 11.